Good morning, everyone. My name is Mahdi Kalaya, and I'm going to talk about human semantic parsing for person re-identification. This is a joint work with Emre Basaran, Moitin Gökmen, Mustafa Kamasak, and Mubarak Shah, and was published in CVPR 2018. Okay, so let's begin with the problem. The problem which we are interested in is person re-identification, which means that given a query image, we want to retrieve all the images from the gallery that are of the same identity. Images in the query and gallery are captured via distinctively different cameras, which may or may not have any field of view overlap. So here, showing an example, the query image and the top 10 retrieved images. The green bounding boxes show the correct matches, and the red ones show the incorrect ones. The problem of person re-identification is a very challenging problem. The first thing is, for instance, we observe illumination condition. Some images are captured under very bad illumination condition, which makes extracting visual information very hard. We have background clutter, we have occlusion, and observable body parts sometimes are not fully visible. For instance, in this example, umbrella is covering the head of the pedestrian. And sometimes the perceived posture is hard to obtain because either, for instance, in this case, there are two people in the scene, or the pedestrian is holding a backpack. Even within a single camera, we have challenges in terms of extracting robust visual representation, because temporally, when a pedestrian goes by, he or she may be occluded by different parts, or from the viewpoint of the camera, the visual information would dramatically change. Because in the gallery we have multiple images of each identity, and each are captured via different cameras, we would also observe intra-class variation within the gallery. And finally, often in person re-identification, the images are of low resolution, which makes it hard to use in modern, for instance, deep learning architectures, because they often operate on very high resolution. So in this work, we ask two questions. The first one is, if we look at the current literature, it advocates for very complex architectures and multiple stages of non-trivial training. So we ask the question whether these complex models are actually necessary in order to obtain a state-of-the-art performance. And the second question is, what is the best way to extract local visual cues? Because the current literature suggests that in order to boost the performance of person re-identification, we have to extract local visual cues from human body parts. So currently, the way which this process is done is using human pose estimation. So you use a human pose estimation, estimate the joints of the body, and then extract local visual cues from those joints. The problem is, human pose estimation performs poorly when the images are of low resolution, and it is unable to capture arbitrary contours of human body parts, because even if you detect the joint properly, then putting a bounding box, which is a rigid box, around the joint is not aligned with the arbitrary contours of human body. For instance, an arm is not a bounding box. So if you simply put a bounding box around it, what happens is that it would contain a lot of background, and your representation would be polluted by that misalignment. The other way is we simply use methods such as horizontal strips that you don't have any semantic alignment, but it's very easy to implement because there's no pose estimation done there. So the contributions in our work is that we propose to use human semantic parsing in order to person re-identification. We call it a sprite. We also show that simple holistic models, no feature extraction from local parts, are able to work very well and outperform state-of-the-art if they are trained properly. We show that we achieve a state-of-the-art performance on 3 different datasets with very large margins. Okay. Let's first talk about the sprite model. We have 2 branches in the sprite model. The first one is the person re-identification backbone, which uses an Inception v3 architecture. It's the standard Inception v3. The human semantic parsing one use a modified version of the Inception v3 architecture. Because we want to do semantic segmentation for the human semantic parsing branch, we want to make sure that we maintain sufficiently large resolution in the activation of the network throughout the entire depths. So to do so, we use dilated convolution and change the standard output stride of inception v3 from 32 to 16 by modifying the stride of the last grid reduction module. But in order to cope with the additional computation costs, we replace the following convolution layers with dilated convolution. At the classifier, we use a pyramid of dilated convolutions, which helps to achieve a better quality semantic segmentation models. So now, let's look at the architecture. Given an image, we pass it to inception v3. Here you can replace inception v3 with any other architecture. The bilinear interpolation is to match the size, the input size to what we intend for the architecture. And we simply get the final activation from it. So now, by a global average pooling, you obtain the final representation, which is a 2048 dimensional representation. That's what we call it a global representation, because it operates on the whole image. And as you can see, this is the standard architecture, nothing fancy here. So now, if I want to extract the local visual cues from the human body parts, we pass the image to the modified inception v3, which is modified in order to do human semantic parsing, and we obtain the final activations. As you can see, the output activations in this human semantic parsing branch is of larger resolution than re-ID branch, and the reason is we need that high resolution in order to get a quality parsing. So now the classifier of a human semantic parsing is simply one-by-one convolution, and after passing it to a softmax, it gives us these labels. So for instance, here we are grouping each pixel to five coarse groups of labels: foreground, head, upper body, lower body, and shoes. So now if we look at the upper branch, we simply aggregated the activation from the entire spatial domain, which means the final representation is agnostic with respect to where the activations happen, as long as you average and the average is high. That being in the global representation would get a high value. But now what we can do is we can upscale the activations of the re-identification backbone and match the resolution to the masks of the human semantic parsing. And now instead of globally pool the activation, pool it using these masks. So what happens is that instead of one representation, you would end up with 5 different representations, each one being computed via masking the upper activation using one of these masks. So as you can see here, if we use the first mask, for instance the foreground, and pool all the activations on the upper branch, you get one 2048 dimensional representation. If you use head region, another representation like that. So what happens is that this can be done via a weighted sum operation, which is simply an element-wise multiplication between the masks and the activations of the backbone. So now, as I said, we have one global representation, one foreground, and lots of representation for each part. So this is the overall architecture of the sprite. Let's look at the training and evaluation details. For person re-identification, we simply use holistic images, and we train the model using softmax cross-entropy laws. In order to achieve a state-of-the-art performance, as I mentioned before, we wanted to know whether simple holistic models work. So here are the 2 tricks in order to train a holistic model properly to achieve a state-of-the-art. The first thing is we have to train it in a large scale. The way which we did it was that we aggregated 10 different re-ID datasets together, and which results in 111,000 images and 17,000 identities. And the other thing is, because those modern architectures which we use here are very deep, what we do is we first train on low resolution, which is not actually low, it's more kind of a medium resolution, and then fine-tune it on high resolution. So these 2 tricks, training on larger scale and training on low resolution, fine-tune on high resolution, these 2 are sufficient in order to give you a state-of-the-art performance. So I would later show the result, but these two, as I mentioned, would confirm that a simple holistic model works. For human semantic parsing, we use an auxiliary dataset of look into person, LIP, and train the semantic segmentation model on 30K images with 20 labels. But then we group these 20 labels together in order to obtain 5 coarse groups. For instance, we group class hat, hair, glasses, and face together to come up with the coarse group of head. The details are in the paper. So now that the model is trained, what we can do is we can pass the re-ID images in the lower branch of the sprite architecture, as I showed in the previous slide, to this semantic segmentation, and it generates those masks, those 5 masks which I showed before. And then we aggregate the features, a global representation obtained holistically, a representation from the foreground, and the body parts. For the body parts, we have 4 body parts. What we do is simply element-wise max them together, so we get one representation from all the body parts. So now you can L2 normalize these 3 representations, each one being 2048, and concat them together. So that would be our final representation, and we can simply measure the query to gallery similarity using this 3 times 2048 representation using Euclidean distance. So the data sets for the evaluation in this work, as I mentioned, for training, in addition to 3 data sets that I'm going to talk about here, we aggregate the training split of 7 other data sets as well. So we evaluate on Market 1501, which includes 6 cameras, and the human bounding boxes are detected via DPM. We do with CUHK03, which is again 6 cameras, each identity viewed by 2 disjoint cameras, and Duke MTMC re-ID, which is 8 cameras, but the bounding boxes are hand annotated. For semantic segmentation, we use the look into person dataset, which with 30K images and 19 labels plus a background. Here you can see example images of different datasets. So let's move on to the experimental results. The first thing is, as I mentioned before, we raised the question whether simple holistic models work. So here we show that if you train the person re-identification model, the holistic model, via the details, I'm just copying it from the previous slide. If you use higher resolution, as you can see on all 3 data sets, we achieve a better performance. So and we are showing it for different rank scores. So this shows that actually you can easily get a boost in performance by simply feeding a larger resolution image to the network. And it's very intuitive, because when you use deep architectures, in fact, for instance, Inception v3, it's 48 layers deep. If your input resolution is very small at the beginning, after a few layers, you are losing the entire resolution of the activation. So you think you have like 3x3 kernels, but they are not actually operating like that. So you want to make sure, for instance, an architecture such as Inception v3, which has an output stride of 32, you feed it with large enough input resolution, so sufficient resolution is maintained until you get to the end of the network. The other thing is train on low resolution, fine-tune on high resolution. Again, I'm showing it for Inception v3 and ResNet 152. So 2 architectures on 3 different data sets, and we can observe that you can get a boost of performance simply by further fine-tuning on high-resolution images. We didn't include it here, but we have the numbers for ResNet 50 as well in the paper. So up until now, we have addressed the first question we asked. For the sprite model, here we are showing the effect of utilizing human semantic parsing, which means that if you compare Inception v3, which is the holistic model, no semantic segmentation, with the sprite model, which utilizes human semantic parsing, and we are showing with foreground, without foreground, and combination of them. We show that our sprite model are outperforming the baseline model without semantic segmentation considerably on all 3 datasets. The other thing is we had this global pooling, which gave us the first chunk of the representation, and the semantic-based pooling ones. If you share weights between the backbone of architecture which extract these features, versus not sharing the weights. You gain a little bit of a performance if you do not share the weights, but the cost which you pay is that the model is larger because now you have to maintain two Inception v3 architecture in your memory. But even with fully sharing the weights, still you can get a very good boost. So comparison with the state of the art, here we are showing it on Market 1501. I'm showing both our baseline models, Inception v3 and Inception v3 fine-tune and fine-tune star, which in the star case, it is concatenated with ResNet 152 as well, and the sprite model. So even our baseline model, which operates holistically when trained properly using those two different tweaks, it's able to outperform a state of the art. The same thing is valid for CUHK-03 and DukeMTM ReID. Here I'm showing some qualitative results. Given the query image, the upper row is Inception v3 fine-tune, which is a holistic model, and the bottom one is the sprite model. Here are some more. As I mentioned, the green bounding boxes means the correct matches, and the red ones are the incorrect ones for CUHK-03. So if your model mistakes, you prefer it to be on the later ranks. So you prefer, for instance, rank 1, rank 2 be correct, and like if rank 10 is incorrect, it's much better than rank 1 being incorrect. So here are for CUHK and DukeMTM. So as you can see that our sprite model, which uses semantic segmentation, performs much better than the baseline. Okay, so here I'm showing some qualitative results on how those masks, which I mentioned for pooling activations, look like. We train our human semantic parsing model and then pass ReID images. Here you can see how the images are parsed into different regions: shoes, hands, lower body, upper body, head, and background. In order to confirm the quality of our human semantic parsing, we evaluated it on the validation set of look into person, just to see how good our network is. And at the time of submission, we were able to achieve a state-of-the-art performance on the human semantic parsing task, despite this was not the main goal in the paper. So in conclusion, we showed that holistic deep convolutional neural networks can outperform a state-of-the-art. You just need to train them properly on large number of images with many identities and use sufficiently large input resolutions. And the performance was consistent across a variety of architectures. If you want to extract local visual cues, it's better to use human semantic parsing because it can capture arbitrary contours of human body parts, and it provides you with pixel level accuracy than rigid bounding boxes using the pose estimation. Then you extract the global features with the foreground and body parts, simply concatenate them together and use them for query to gallery similarity. Thank you.